Hi, it's Jacek again. I hope that you can hear me. Okay, thank you. So the next presentation, next course is a very special one. I will try to introduce you with some fundamental concepts related to machine learning. So we will travel from a simple regression or from a simple formula to artificial neural networks. And this is the agenda for our course. I will try to introduce you with all these concepts or even more. This is very ambitious, as you see, but I will try. Okay, first, what is artificial intelligence? Well, for a simple illustration, we try to map human intelligence to a machine. So what is human intelligence? Well, there's a lot of different definitions, and my task is not to define what is human intelligence. I would just put it simple. Human intelligence could be some set of capabilities or abilities of a human being. Artificial intelligence, capabilities or abilities of an artificial object. So we would like to introduce the intelligence to the machine as a well-known rule. So we will build a knowledge-based AI. For example, we know the model how to calculate displacement based on velocity and time and initial displacement. So we can program such kind of procedure in a computer, and we can provide some parameters and so on and so on. So this is very simple. Another form how we can introduce the intelligence to a machine is we can introduce a procedure to learn rules. So to learn or use models to learn parameters, that would be database AI. In general, machine learning, which is sometimes defined as a part of artificial intelligence, machine learning aims to teach machines how to learn and act without being explicitly programmed. We will cover some issues related to machine learning. So now we will learn a few new concepts. For data-driven AI, we need data. So for example, X is independent variable, observation, Y response variable. Using such kind of data, we can present a simple illustration like that. And based on some experience, maybe, we can propose a model. The model that could be described by a formula. And our task could be to find out the parameters A and B of such model. Of course, we can calculate such parameters using a set of equations. And it is not a very difficult task, as you can see. And of course, we will get the parameters A and B, and we can use these parameters and the model for future prediction of independent for a response variable. So for example, we have a new value of independent variable X, observation 3, and using our model 10 multiplied by X plus 0, we can predict, of course, the value of Y, which is not, of course, very difficult. So in the data-driven AI, we need data and learn models and parameters. For the scope of this course, the model is proposed, and we will not try to learn the model. We will try to learn parameters usually for the model. To get data, we can perform some experiments, measurements. For example, we can measure the distance for a car after some time. And we can do it for different points in time. So for example, our car will travel, we will measure distance and time. So we can get a set of measurements. You see, we have 5 rows. We know the model. So then we can try to use such kind of data to find out the parameters of this model. What if our measurements are not accurate because of some noise? Of course, then we probably will try to estimate the parameters. So once again, we have our data, but first start to propose a solution for a model using first two rows. So we can use sample 1, sample 2. Then if we solve the set of equations, then we can calculate parameter v and parameter s0. So v would be 12, s0 minus 3, for example. And then we can use the sample ID number 3 just to find out the distance. So for example, 12, this is our velocity, multiplied by 3, because in a row 3 time is 3, minus 3 because in S0 is minus 3. So the result of the response variable is 33. But please look that in our measurement we have 28. So there is clear difference between 28 and 33, and we can somehow calculate the difference to find out that our model is not perfect. And of course, we can calculate such kind of error measures using different formulas. For example, we can calculate absolute error, square error, mean absolute error, mean square error, root mean square error, and so on and so on. For our simple data set with 5 rows, we could split our observations, so measurement vectors, into 2 sets: the training set and the test set. Just using the previous slide, we use 2 first rows as a training set to find the parameters of the model. And we used the row number 3 as a test set to calculate some error. So now we could also calculate the error using, of course, not only one vector, but all 3 rows. So row number 3, row number 4, row number 5. And we will find out that our, for example, root mean square error will be 5.5 or something. We can also use another notation using the samples from the training data sets. Of course, 9 minus 1 will be 0, 21 minus 21 will be 0. However, we are dividing by 5, so this is another, let's say, possibility. But usually we are not using a method like that. We're using only test data to calculate our error. In linear regression, we will not use only 2 samples. Usually we are using much more samples to estimate the parameters. How we can calculate those parameters using more than 2 samples? Okay, very soon. But first, let me introduce another version of our notation. So our model y equal ax plus b, we will change into another model, v multiplied by x plus b. So as you can find out here, we can also reformulate that model like that. So we have 2 parameters, x, and another x is just a constant value 1. So we can also reformulate this formula like a sum over x using j as an index. And we can illustrate this operation as this very simple graph you can see here. We have input elements like 1 and x1. We have parameters w0, w1, and we have operator. And then finally we have result y. Okay, so now maybe we can make some experiments with first notebook. So let me go to the first notebook. You can see here. So I'm using NumPy for numerical operations. I'm also using matplotlib, the library for plotting. So let's start this cell. In the next cell, I'm trying to define a very simple model just to generate data. The data that will be used as a training data set for future models that we will use. So the model is very simple. is, as you see here, plus some noise. So far, I will use noise equals 0. So my parameters I like here. I will try to generate 100 samples. Okay, so let's execute this cell. Then I will try to generate 100 X samples using random generator with a data elements of type float. Then I will sort X values. This will be only interesting for plotting, just to get an interesting plot. And finally, I will try to calculate the response variable values using my generated X values and the parameters. Okay, so let's do it. I can print the values that I just generated, you can see here, but I can also plot these values. So I'm using some setting for font size, and then defining my feature. And finally, the most important code is here. Just plot our data using X and Y and the black color for plot. So this is our plot. Of course, if I will introduce some noise, so let's come back to noise definition. So instead of noise equals 0, I will add some noise, again using some random generator with some modification of amplitudes of noise, so you can perform different experiments. Again, and I will regenerate all the cells just to show how the values will change and also the plot. So now you can see that my data are really are corrupted by noise. We will use this later in the next steps of our course. Okay, so let's go to the next part. We are talking about regression. What is regression? Regression means that we are falling back to less perfect state. So means that regression from a lot of data, usually we will get less data, some parameters, some values. Regression, it could mean that we will get some simple values like mean value, which you can see here for our data, or we can try to find out the parameters A and B. You can see here, that's like an estimation of the unknown true value without noise. Using some well-known mathematics, we can calculate the values of parameters for this regression. However, we would like, in this course, to find out these parameters using some iterative procedure, using learning from data. Okay. So how to find such parameters using such kind of methods? We need an algorithm that will fit the model to data. Such algorithm will assume that we need certain starting values of the parameters. We need a method to change those initial values, and we need a specific criterion. Okay. So maybe we can make some simple experiments. Let's play a simple game known as Guess the Number. Computer, I chose a number, and the player doesn't know this number. So, computer, a number is from 1 to 10, and it is an integer value. And the task or goal of the player is to find out the number, to guess the number. So the first initial guess is it 8? Well, the computer answered, no, too big. Okay, so the player, is it 4? Please notice that the player just divided the value by 2. Computer, too small. Okay, so another proposal from the player. So it is between 4 and 8. Maybe let's do the update. 4 plus And please see that the player updated the initial value by some another value. So it is 8 minus 4 by 2. So 6. Is it 6? Well, what about that? Computer, too big. So now, again, our clever player is trying to find out next update value. So 4 plus 6 minus 4 divided by 2, 5. Is it 5? Well, perfect. This is the proper answer. So as you see, in this very interesting game, our player used some kind of method, something related to dividing the value or the update by 2. So how to make it more algorithmic? How to find the best parameters? Instead of guessing, we can search the space of possible solutions using more clever way. So our task will be to find x at which a given function is minimal. Instead of the brute force method, when we can try all possible values, that would be very difficult because we have real numbers here. So we need some clever algorithm. For example, we could start from initial values and introduce some update using a specific rule. So the current value x can be modified by introducing some update, delta x, with some scaling factor. So the new estimated value of the parameter will be calculated using such kind of methods. What is this delta x? Delta x is a gradient of a function y at the point xn. So if our function is like that, x squared, of course we know that the derivative of this function against x is 2 multiplied by x. So starting from initial x, we will modify this value x using just value of minus 2x. Well, maybe this is difficult, so let's stop for a moment and make a simple illustration. Our function is x squared. Our initial value for the parameter, so the x, is 4. We are going forward, so we are trying to calculate value of our function at x. So 4 squared is 16. So it is illustrated in the graph. Now we are trying to calculate the gradient value. We will estimate that using this formula. So that's why we need to calculate the value of the function at x plus 1 and x minus 1. So let's assume that x plus 1 is 3, x plus 1, x minus 1 is 3, x plus 1 is 5. So we can then calculate the value of the function for 3. So 3 squared is 9, 5 squared is 25. And now we can calculate the gradient. So the gradient is 25 minus 9 divided by 2 is 8. So using the formula that I introduced before, we can update the current value of the parameter using our gradient. So in this case, we have the current value of the parameter is 4. 4 minus 8 is minus 4. So the value of our function at minus 4 is 16. Minus 4 multiplied by minus 4 is 16, of course. Well, this is not minimum. Let's try again. We have minus 4 now because this is the current value of the parameter at this step 1. We are repeating exactly the same operation and we are updating the value of the parameter just to get the new update. But as you see, the new update is 4. So we are again with the value as it was at the beginning. So actually, we will have infinite loop and we have no solution. So how to modify this procedure? As you remember, before, I introduced a special scaling factor. So I will update my initial value of the parameter with the gradient of the function against the current value of the parameter, but first I will multiply that by some scaling factor. Okay, let's repeat our experiments. Again, we are starting from a value 4. The calculations of the gradient are exactly the same. However, the upgrade now is different because we are multiplying the value of the gradient 8 by our learning rate. So 0.5 multiplied by 8 is 4. So 4 initial value minus the update 4 is 0. We have the minimum value. Wow. So we were lucky because we actually guessed the best learning rate value for these experiments. What if we are not so lucky? What if we will use another value of the learning rate, for example, 0.05? So again, we are starting from initial value 4, again the same calculations, but now we are multiplying the gradient not with 0.5, but 0.05. So as you see, now we have 4 minus 0.4. So the next step parameter value will be 3.6. Of course, the value of the function at this point is lower than it was before. We can repeat the experiments for the next step, again. So we will actually go from the initial value at x0, we'll go down to the next value, and again next value, and so on. So as you see, we are going towards our minimum. Okay, great. Let's do another experiment using our code. Okay. So this is our another notebook. Again, I'm trying to import the required libraries, NumPy. Then I have the definition of function that will be used to plot our results. You can see how it looks like. I will not describe this function because it's only used for illustration. I am defining the model. My model here will be x squared or a squared because I'm using another name of the parameter. Then here I am calculating derivative. Well, this is another function. I will not calculate numerically. I just know that this is 2 multiplied by a. My initial point for x will be 4, and the value of y for the model and for this initial point is calculated here. So let's execute all those cells again. Now I will define some additional parameters. I will define the scaling factor, which is called learning rate, like 0.05. I will define another parameter, which I will call precision. I will come back to that later. I will set the variable x equal to the initial value of x, which is 4. And I will define some step size. Now I will assume as a step size the absolute value of x. Again, I will describe that later. So my data set is defined here. I am defining this data set as a NumPy array because I will update the data set with my data in each step when I will calculate the new y based on the new x. Okay, so let's define the procedure. I will introduce another variable, just a step counter. I will initialize as x minimum xs, y minimum as current y. Of course, I will assign new values in my training loop just in a second. And then I will define my training loop. What is this training loop here? I would like to execute this set of operations until the step size is bigger than precision. What is the step size? You can find that step size is defined here. It's absolute value between the current value of the parameter and the previous value of the parameter. I just defined the, let's say, condition like that, but we can define another conditions how to end this procedure. For example, it could be the total number of iterations. It could be some criterion for minimum value of the y function, and so on. So my procedure is like that. Let's remember the previous value of the parameter. Let's update, so we can do like that. Let's update the value of the parameter using the previous one, using the derivative calculated for the previous one, multiply by our learning rate. Next, of course, we are calculating the step size. If the step size will be very, very, very small, it means that, well, maybe we should stop our procedure. Then I'm calculating y using the actual value of x. If the current y is lower than so far minimum value of y, I would like to remember the value of the function and the value of the argument. I would like to also remember the current value of y and x and add it to my data set. Okay, so let's execute those cells. As you see, I am printing the values. So please look carefully. After the first step, the actual value of x is 3.6, exactly the same as it was at our slide. Next step, 3.24, and so on, and so on, and so on. You see, we have many steps. We are going toward our solution. And now I would like to show the solution using plotting procedure. So I will execute the next cell. In the next cell, I am printing the last value of y, so the minimum value of y and f, and x for this minimum value of y. I will also print the total number of iterations, and I will try to plot my results, so data set, all the calculated x and y values using the plotting function I prepared. So let's do it. You see, so this plot illustrates that I started from the initial value 4 and I just travel toward the minimum value. Of course, I can choose another starting point. So instead of 4, I could use -5, execute this one, recalculate everything from that point, start the learning procedure again, and illustrate, show our results. As you see, I started from -5 and I'm going to my minimum. Okay, so let's focus now. Okay, now we can go further. In a simple regression procedure, we will use very similar methodology, but now, of course, we will look for parameters, not arguments like x. our task will be to modify the values of each parameter from the previous iteration, introducing some positive, negative change. And of course, we need now some error measure to verify if the current value of the parameter give us, let's say, different error value than previously. So we will use the training data set in the training phase, and we will be looking for such parameters that such error measures that we will call cost function or loss function will be minimal. Okay. So our regression function is now something like that. We have parameters W. So we want to find parameters W at which the cost loss function is minimal. Okay. So we are looking for the optimal value of parameters W for a specific loss function. We are providing this loss function training data, X and Y, and initial values or previous values of parameters. As a loss function, we will use mean square error. Ym means true values or values from measurement. Y means values that are estimated. So again, using a very similar methodology, we are looking for the new value of the parameter based on the actual value with update. The update is calculated again as a gradient of the loss function, because we are minimizing the loss, the cost, the error, scaling using our scaling factor or learning rate. So again, we can go to a very simple demonstration. So once again, I would like to import my libraries, but additionally, I would like to show you how we can use symbolic Python library just to find out symbolically the derivative. I'm also using some special module, lambdify, that we can create a function from the symbolic representation of the gradient. So let's import that. Okay, now just to illustrate how this symbolic operation work, we can just define what are the symbols that we would like to use, X and W. Okay, so we are using our module for symbols. Then we are defining the operation here, the operation, which is actually, in this case, derivative after W. So first element is a formula. Second is a parameter. So this is derivative after W. As you probably know, the derivative will be just X. We can print symbolic solution. We can also define a function using this lambdify function from our module. This lambdify function, first, we can specify the parameters, the arguments of the function, the definition of the function in the symbolic form, and of course, how we will represent our data. So in this particular case, we can define data as a one-dimensional vector, 2 and 3, and we can execute the function f, specifying as an argument the values x, and so this is value of x, and value of the parameter. Let's execute that. The first result, x, is a result of printing our symbolic solution for this formula. The second print is, of course, operation result of applying the result of this function, of this derivative after W operation. So we have just X. So if we are specifying 2 and 3 and our parameter W is not used actually here, we can of course change the definition of our function. For example, let's square the W parameter. So now our function is X multiplied by W squared. What will be the derivative? What will be the value of the function based on this derivative? You see, the derivative is 2 multiplied by W multiplied by X. So now our result of the function based on this derivative is like that. Okay, so let's continue. This was only a simple experiment. Now, I will use also a simple plotting function to plot our results. Again, as it was before, I'm defining my model, but now as you see, my model is X multiplied by W again. I'm specifying my loss function, which is a mean square error. I have Y and estimated Y. Then I'm specifying the function to calculate the gradient using this symbolic module. As you can find here, I'm defining 4 symbols. X, which is our independent variable. W, it is our parameter. Estimated Y, and let's say observed Y. This is our model, X multiplied by W. This is our loss function, so the difference between true and estimated response variables squared. And I'm calculating the derivative for my loss function in respect to parameter W. And I would like to print this symbolic representation of my gradient. Finally, in the same function, I'm trying to define function from the symbolic representation of my derivative. As a result, I will call the just defined function to calculate the gradient. Finally, another function, which is here, calculating the mean, because we would like to use mean, not only a set of values of functions for particular X values. So let's execute this cell. Nothing is presented because there are only definitions of functions. Let's illustrate how this function works. So we will define some parameters. Let's say initial data X, initial data Y. So as you see for our model, X multiplied by W equals Y. We see that probably the true value of W is 1. Why? Because Y is equal to X. 0, 0, 1, 1, 2, 2, 3, 3. But we don't know that, let's say. So we will try to guess the initial value of the parameter, let's say 5. Let's guess it. Now I'm trying to print all these, let's say, values. So the true values of ys, initial value of y, then the value of the function calculated for an initial value of our parameter w. Then I would like to calculate the gradient, calculate the loss, so I will call the loss function and print the cost value. Okay, so let's calculate that. Okay, so as you see, the first line represents the true values of our response variable, so y, 0, 1, and so on. Then the next line presents the results of our model using initial value of the parameter w, 5. Yes, true. 0 multiplied by 5 is 0. 1 multiplied by 5 is 5. 2 multiplied by 5 is 10. Oh, so it's correct. the next slide presents the symbolic presentation of our gradient and the application of our operation and the cost. Okay, so now we can use our functions that we already defined, so the loss function and the gradient, for our training procedure. The first actually rows or lines of this code are very similar as it was before, but now I'm trying to change the, let's say, stopping criterion of this training loop. I will try to train my parameters using 50 iterations, epochs. I will also try to remember the cost in each iteration. So let's start again. Our previous value of the parameter is, let's say now, the current value, initial value of the parameter. We are introducing the update to a parameter, so previous value minus eta, the learning rate that we defined, and the value of the loss function calculated for our training data, x, s, and ys, and the previous value of the parameter. All other is practically the same as it was in the previous example. So let's execute that. Well, what we can see here, again, we can see each step and the progress of our learning procedure to find out the W parameter value every time we are presenting the cost. So as you can observe here, the cost is lower and lower with each step of our procedure. I am here plotting the loss value for each iteration. As you can see, the cost is lower and lower. And again, I can plot my results. Okay, I have to execute this plot function definition. Okay, and now again, I can execute that. So again, as you see, we started from the initial value of the W parameter 5, and then step by step, update by update, we change the W parameter to obtain the best solution 1. Okay. So now you can see that really it is not so difficult. The formula, the definitions, well, may be complicated, but it is not so difficult. Okay. So this is our, let's say, loss function. And in our iterative procedure, we just change the values of parameters proportional to the derivative of the loss function in reference to parameters. If we have only 2 parameters like here, like in this example, then we can even analytically calculate the derivatives. So if this is our, let's say, cost function, then we can find out that our derivatives, concluding that this is also the, let's say, operation of averaging here, of mean, so that is why we are summing that here, we can find out that derivative of that function is just simple against, so in reference to parameter 0, so this one is like that, and in reference to parameter W1, it will be something like that. I think that it's not very difficult to calculate that using a chain rule. Okay, so actually now we have our procedure. We are performing some iterative operations to update the previous values of our parameters. We're calculating the update, and we are looking for some criterion. That could be, for example, let's say reaching the number of epochs just to find out the, let's say, difference between previous and actual value of the function or the step. So we are looking for the, let's say, some condition C that should be reached. And until the condition is met, we need to update our parameters. Please notice very important aspect here, that calculated our update, we are using all samples from our data set. So if we have M samples, we are performing the operation for all samples here. If you are using all samples like that, this algorithm is called batch or full batch gradient descent. Gradient because, you know, we are using gradient. Descent, of course, we are going towards the change of the gradient. You see minus gradient. And batch, full batch, because you are using the total number of training examples. So this is a definition of gradient descent or full gradient descent algorithm. Let's go further. Of course, instead of implementing everything as a code in a Python, usually we are using frameworks. There are different frameworks that are used for machine learning. For example, TensorFlow, PyTorch, and so on. For deep learning, usually we are using TensorFlow, PyTorch, or other similar libraries. I will use in this tutorial TensorFlow. What is actually TensorFlow? TensorFlow is based on two concepts. First, tensors. Tensors are multi-dimensional arrays, 0, 1, 2, etc., to store data. Operations are a collection of functions that are performed on tensors. So there are the most important concepts for TensorFlow. Well, there is a question, is the framework better, TensorFlow or PyTorch? There is not a universal answer for that one. I think it depends on many factors. I think that it could be a subject for discussion later. Okay, TensorFlow offers two execution modes, graph mode or eager mode. Graph mode is a special execution mode that you are building a graph that is consists of tensors and operations. It's like preparing the whole procedure, the whole operation, the whole program, and then compiling the program, providing the values of parameters during the execution. So after the definition of the, let's say, graph mode, after the definition of tensor and operations. Another execution mode is eager mode. This eager mode was introduced recently, especially it's a, let's say, a default mode for TensorFlow 2, and it's like a method that all operations are executed immediately, like interpreting the operations. During this course, I will use eager mode. Okay, so now we have all elements to try to execute our procedure for regression operation. So let's start another notebook. Okay. Once again, now I'm starting from importing the required library. However, additionally, I am importing TensorFlow library because I will use it. I would like to print the version of the TensorFlow library that I will use. So let's execute this cell. You see, 2.3, this is the version of TensorFlow I'm using from Google Colaboratory. Now let's introduce some basic TensorFlow elements. Okay, so I will try to use two variables, so two tensors actually. The first tensor will be, one moment, the first tensor will be to store information about parameter W or a set of parameter W. The size of this parameter or the shape here is defined and actually initialized using zeros as n by 1. But I define n as 1. So actually there will be only one parameter. I define this variable here just for the next example that I will present to you, when the value of n will be not 1 but larger. So just for now, there is only one variable for storing, let's say, w parameter. This function is actually the same as in NumPy. I'm initializing the parameter w with 0. The same for b. Just for an example, I'm initializing it not with 0, but let's say 1. Why not? Just for learning. Then please find that I'm defining two functions. The first function, I call it forward eager, forward, because I will use it to perform forward operations. It means providing x and having current parameters calculate the response value, so the result of the function. The next definition is forward graph. So please find that I'm using additionally here some decorations, some additional annotation for a function, and this decoration means that automatically this function will be defined in the graph mode. I'm only using this here just to compare how the difference for defining function could be. I will not come back to that later. Okay, so we have the function, we have variables. I can specify some initial value for x, and I can execute my functions. I can even compare the time required to perform operation of those two functions after, let's say, 10,000 iterations. So let's present that. What is very interesting here? Please notice that I printed here the result of the forward function execution for eager and graph mode. But each time I just receive something like that. This is the tensor object with values 1, 1, with shape, let's say 1 row, 2 columns. Data type is floating point with the precision 32, let's say, bits. Just for this very, very simple example, the eager mode is faster. But usually, if you are defining the more sophisticated model, the graph mode is better, is faster. Okay, but let's go further. Now it's a very important aspect, so please focus for a moment. Again, I'm defining learning rate that we will use in my training loop. I'm just to visualize the example, defining some kind of, let's say, training values for y, 2 and 4. I'm defining my loss function. This is a mean, but since I'm using TensorFlow operation, I'm defining this function in reference to TensorFlow functions. So first of all, just square the difference between measured and estimated values and calculate the mean, reduce, so I will get one value for a loss function. Then something special for TensorFlow 2. There is a special, let's say, function, gradient tape, that is calculated with a special context. So this gradient tape is used to calculate, let's say, to execute forward function and to remember the state so we can get gradients. So this gradient type is used to calculate gradient later. So we will remember everything that was calculating using the forward operation just to later calculate the gradients. We don't need to calculate gradients by our own symbolic functions or just to get the gradients analytically. We will calculate the gradients just using numerical functions. So within this context, to remember all the operations, we are calculating the loss for true values of y, just to calculate the value of x using the same forward function before and x the same as it was before. Then the next line is that we are calling the gradient. So using this t for this context of gradient tape, so we recorded, let's say, our context, calculating all the parameters, so we can calculate the gradient for parameters specified here for the cost function that was defined before. And as a result, we are calculating our gradients. What we are doing next in this cell? In this cell, I'm printing the results, and I'm trying to update W and B, just assigning the new values and subtracting the values from the previous value. So as you remember, the update is like that. Gradient multiplied by learning rate, and subtraction, so minus. The same for both parameters. Please also notice that I will print my W and B parameters using two methods, just calling directly W and W.NumPy. What will be the result? Okay, so the cost function is, let's say, 5. Gradients are presented here, -7, shape -4, and so on. Current, so the result of this now, okay, is current W parameter is, you can find 0, 0, then 0.35, 1.2, and then printing just not as tensors, but as values represented using NumPy, we just received arrays. Okay, so this was only to illustrate how we can calculate gradients using TensorFlow library. But of course, we are more interested in, let's say, learning procedure for our problem. Okay, so now we can use the procedure that we started at the beginning to generate some training data. This is the code that we previously used to generate our training data, to generate synthetical data. Do you remember that? I hope so. And now I can define my true training loop using, let's say, TensorFlow. Again, my learning rate, let's say, 0.05. Number of epochs, let's say, 500. What is a batch size that I'm specifying here? Batch size, in the method we call full batch gradient descent, we are using all examples from the training data set. Our training data set is 100 samples. If I use less samples than full, let's say, size of my training data set, I'm using smaller batch. I will comment that later. So now I'm specifying a variable batch size 10, smaller than, let's say, entire training dataset size. Again, I have only one parameter W. I'm defining again my parameters with some initial values. I'm defining the list for Python just to store the loss values in each step of my procedure. I'm defining the training function here. So again, this is, of course, the name of the function, and then there is a proper loop for a function. For epoch in epochs, so I have 500 epochs, so I will perform this loop 500 times. As you remember, if you would like to calculate gradients, we will execute this formula to remember the operations, forward operations. that can be used further, this data from this operation, to calculate gradients. Now we can consider two cases. First, if the batch size is the same as the full dataset training size, then actually we are calculating only the cost here, the same as it was previously. So we are specifying the true training y values, and we are calculating y values for our x. However, if our batch size is lower than entire data set training data set size, we have to find some subsets or a subset from a data training set. In this case, what I'm doing, I'm trying to choose some indexes from indexes to the entire data set. And then using those randomly generated indexes, so my batch size is 10, so I am generating 10 indexes from this range. And then using those indexes, I'm trying to get X and Y data for our batches. So what is the conclusion? I'm not using the entire training data sets, but subset of data, actually only 10 samples. And this is a very simplified training procedure because in one iteration, I will use only 10 samples from the entire data sets, randomly chosen from the entire data set. Okay, so my cost is calculated, so I can calculate gradient in the next operation exactly the same as it was presented earlier. Again, I will update my parameters using the calculated gradient and learning rate and print the results. And also I will store the cost value for each iteration. Okay, so this is the definition of my training function, the loop for training. Now I can call this function and I can print the values of parameters. So let's execute that. Oh, I should define everything again. Once again. So run everything. So once again, I'm executing every cell. Okay. And now this one, generation of data. I generated my data, so now I will receive my results. You see here, one moment, I will scroll it because we have a lot of 500 iterations, you see. So let's say epoch 365. Then we have our cost or ROS, and just iteration by iteration, we can observe what is the difference. See, until we reach the final iteration. Please, what are the final results? W 0.2 something, B 0.almost 4. So you can find out that really we reached almost identical, very similar values of our parameters W and B that were used to generate, please see here, to generate our synthetic training data. Wow, perfect. So our training procedure works. We just learned our model just to find out those parameters. Let's illustrate the results. The next cell is a set of instructions that are used to plot our data. Maybe I will execute this cell. So you can observe that the first plot is our, let's say, original data set. The next plot is the model that we just obtained. The model described by those parameters. Here is a W and B. The true was 0.2, 0.4. We obtained something like that. The next plot is a difference between the obtained model and the, let's say, true data. And of course, the last plot is our loss function plotted here, loss values presented for each epoch. Okay, but let's change everything maybe, just generating or using some noise. Not noise zero, but again, we will introduce some noise. So let's generate our training data. You see, again, we have a lot of noise. And again, let's execute our training procedure. 500, let's say, see? And once again, present our results. You see, we have really our true data with noise, but our model looks quite fine. You can perform your own experiments, specifying different levels of noise, and just specify different parameters, and just to find out what will be the results. Okay, that's fine. But let's go further with this example. What I did is I propose to define the learning procedure, the training loop, and the model using TensorFlow, let's say, elementary functions. But TensorFlow has a very interesting high-level API, which is called Keras. And we can use this high-level Keras API to repeat our operations. So first, we will define our model. So this is the definition of our model. So I will trying to define a class. I will call it, for example, simple Keras model. This is the, let's say, base class that I'm using. So I'm using the predefined model from the Keras library. This is the init function when I'm creating the object from this class. So the init, like initialization, I will specify the n again, like a number of variables, and again, two variables, w and b. Please notice the same definition of variables as before. Now, according to this model, to the API, I'm redefining the call function that will be called when I will use and when I will create the object of this model. This is forward function. So I'm just specifying w multiplied by x plus b. Please notice that I'm using self because I'm referencing to the instances that belongs to that object. And x is an argument. X is actually our training data set. So this is my class. I'm then using this class just to create an object of that class. Then, according to Keras API, I am specifying parameters for training, So I'm doing that in the compile function. The compile function has many different parameters. You see here, I'm showing the help information for this compile method, optimizer, loss, metrics, and so on. Here I'm defining that I will use eager mode for TensorFlow. As an optimizer, I will use stochastic gradient descent. So the gradient descent version when the instances will be randomly generated from the full data set, and probably some batches can be used. I will use loss function, and my loss function will be mean squared error. Please look that I'm not defining this function. I'm using this function from functions available for losses module from the Keras API. So I define everything. So now it's time to start to execute the training procedure. And I can do that executing the feed function from API of Keras. What I have to specify? X and Y, so my training data, the number of epochs, let's say 300, and the size of batch size. You see, batch size 50, so lower than my entire data set. And finally, after all this procedure, I can present the final values of W and B. So let's execute this entire cell. You see, there is information, epoch, how long it took, what is the current value of the loss function. And finally, we have the estimated values of W and B. Wow. So instead of very sophisticated code as it was before, all I need is this part, this cell, to define the model, to use the model, to specify the parameters for training, and to execute the training function. The end of the story. So let's come back to our slides. Okay, so concluding, if we are using less examples and we are generating less examples using some, let's say, random selection, we are referring to such methods stochastic gradient descent. If we have a subset of data generated using such method, we sometimes call it mini batch gradient descent. What is the best size for the mini batch? What is the best value for learning rate? Actually, we don't know. We are not optimizing our model in reference to those parameters, so we are usually guessing those parameters. That's why such parameters are called hyperparameters. Of course, there are methods that we can learn, we can look for such kind of parameters, but this is outside the scope of this lecture. Referencing optimization. So far, we learned that we are updating our parameter using just a simple gradient multiplied by some scaling factor. But of course, there are some different other optimization methods. One method is called momentum optimizer. What is the difference? Please look here. The update for the next step is calculated as the parameter momentum update parameter, so another hyperparameter, previous update. So you see, we are using the previous update and minus the gradient. So actually, the final update is learning rate multiplied by the calculated update, and the calculated update is based additionally on the previous update. That is called momentum, yes, because we remember about the previous state. So this is very, let's say, popular optimizer. Another version of optimizer, another version of this, let's say, momentum-based optimizer is Nesterov's accelerated momentum. What is the difference? Difference is that we also calculating the derivative, we also, let's say, remember about, let's say, the previous update and the, let's say, other option. What next? Adaptive gradient with decay, another method, another optimizer, very interesting. What is special for this optimizer? We are introducing a new parameter, j. So the j for the next step will be based on the j from the previous step, multiplied by some scaling factor, and plus 1 minus scaling factor. The scaling factor will be between 0 and 1, and the gradient. So the update that will be calculated now is like that. Learning rate divided by this value. This is additional, let's say, epsilon. This is only a regularization factor when this would be 0, multiplied by derivative. So please look at this one. This is very important because what we are doing here, actually, we are dynamically changing the learning rate in each, let's say, iteration. So learning rate is modified. And finally, even more complicated would be another, let's say, another optimizer, which is called Adam. Adam is one of the most popular optimizer currently used, I think, probably, and it is calculated like that. It is a combination of the, let's say, adaptive gradient with decay, so RMS prop, with some momentum-based, let's say, issues. So we are calculating another parameter like momentum for the next, let's say, step, remembering, of course, this is the previous step, should be previous step, and the, let's say, derivative. This one, the G, is the same as for the RMS prop, and of course, again, we are updating the learning rate using these parameters. Well, maybe very complicated, but it is very important that you remember that there are different, let's say, optimizers that we are using in the learning procedure. Well, so now it's very important to go further because we are still in the linear regression and we have a lot of issues and not a lot of time. So what if we would like to perform operation when we have different y values for the same x values? Please notice here we have x value 20, 20, 20, 20, 20, and y is 19, 20, 20, 20, 21. The mean value of y for a specific x is 20. You can simply calculate that. So just drawing such kind of case, you can see that for a specific x, x2, we have different values from measurements, from observations. Why? Maybe this is due to some kind of noise. So actually our y value is represented by those true, let's say, the values that could be estimated using some model and some noise. Okay, so now what if y is not described by the Gaussian distribution? For example, if values of y are bounded, then the change in x could produce no change in y. So for example, we have the following situation. We have the parameter BMI, so body mass index, for example, different values. So this is our independent variable. And our observation is if the patient has or not a disease. 0, no disease. 1, there is a disease. So how we could apply now our, let's say, linear method, linear regression, how we should modify our linear regression? We can use the generalized linear model. Just in short, generalized linear model is described by 3 components. A random component is required that is represented by some kind of exponential distribution or family of exponential distributions. For example, the Gaussian distribution is an example of exponential distribution. Then we need a linear predictor. We know that, the linear predictor. This is our linear predictor. And the link function. Link function that will somehow relate our linear predictor with some parameter. What kind of parameter? Okay. Let y be a discrete random variable with possible values 0 or 1. Oh, our disease, for example. Let p be a parameter with values between 0 and 1. And let's assume that y has a Bernoulli distribution with parameter p if its probability mass function is. Probability of y is p if y is equal to 1 and y minus p if 0. The expected value for Bernoulli random variable y is mi p. So for us, for example, you see that there are 2 cases, 2 examples with x 20 and 20. For one case, the probability is 0, or sorry, the not probability, the result, the this is 0, another is 1. So what is the probability? Let's say we can simplify that it will be 0.5, the probability that the person will have a disease. I will skip that. This is only the proof that the Bernoulli distribution is from the family of exponential distribution. But what is important? Our link function here that combines the probability with our, let's say, linear predictor is like that. Is logarithm p divided by 1 minus p. Please notice, range of p, let's say probability, is from 0 to 1. Range of p divided by 1 minus p is from 0 to plus infinity. Range of logarithm p divided by 1 minus p is from minus infinity to plus infinity. So the range is similar as for our linear predictor. That is why we can say that our link function that we will call logit of p divided by 1 minus p, which is called odds or the chance, is described by our linear predictor. So this is logit. The inverse definition of this one is called sigmoid. It is 1 divided by 1 plus exponent minus this linear predictor. So this one. How to illustrate that? Please notice that this illustrates our odds. It's going to infinity if p is 1, because p divided by 1 minus p, if p is 1, then we have 0 here, so the entire, let's say, equation is going to infinity. Log it is used to convert values from 0 to 1, so our probability, to minus infinity to plus infinity. Why sigmoid, you see S-like shape, sigmoid is used to map values from minus infinity to plus infinity to the range from 0 to 1. So, concluding, if we introduce such function here in our model, sigmoid function here, we will have the non-linear operation when our result will be from 0 to 1. So we can learn the parameters to get the probability, I would say. Okay, so let's go now to the example with some interesting images. So those are the examples from the modified NIST database. This database consists of 60,000 images, with each image with resolution 28 by 28 pixels. Those images represent scanned digits written by different people. And for each image, we have a true label. For example, this is 7, so true label is 7. This is 3, true label is 3. We can use from TensorFlow some TensorFlow dataset module function to load such kind of database. This function will return training and test datasets. So we will get many cases for training and many cases for test datasets. So in this case, what we are actually trying to perform, each image will be flattened to get a one-dimensional vector of pixel values. So instead of 28 by 28, we will get 784 values, x. 784, let's say, input values. Then we have the same number of parameters, plus 1 for our b. Then we have our unit to sum all values. Then we have a sigmoid. Let's say the sigmoid that will be used to get the value of, let's say, probability if we have or not have a specific, let's say, label for our input data. So again, we will now try to introduce the binary classification operation. Why binary? Because this is a simplified method. We will divide all 10 classes, 0, 1, 2, 3, and so on, into only 2 classes. So for example, all digits, all images with digits from 0 to 8 will be class 0, and all digits with the digit 9 will be class 1. This is operation from NumPy that is trying to use new categories of our data. So please look at here. I'm trying to, where y is lower than 9, put label 0. Otherwise, put label 1. Okay? So now I'm trying to generate my data set with labels 0 or 1. 1 means 9. 0 means digit between 0 and 8. And what about the code? Please look at this code. The code for the model is practically the same as it was, or similar as we used before. Now the number of parameters, W parameters, is 784 instead of 1. No other changes. Then the call function reduce sum, so the forward function, and additionally I'm introducing sigmoid function. So the result of this linear predictor will be argument to our nonlinear sigmoid function. Then what I'm doing next? Next I'm performing executing the calling the model, specifying the parameters for training. So use eager mode, specify the optimizer, now still stochastic gradient descent, use the binary cross entropy. I will tell you what this binary cross entropy is in a few minutes, and introduce additional metrics, mean square error. And of course, I will execute this operation after a few seconds using an example. Additionally, I can use some metrics to calculate or to execute our model, to check if the model after training is okay. The Keras API provides two interesting functions. Evaluate, so we can provide test data sets and obtain the loss or other metrics values. Or we can do this, let's say, verification using our own method. So we can predict the label using test data set, and we can compare if the predicted label is, let's say, similar to the labels from the test dataset. Okay, so now it's time for a short demo. Okay, so what about this example? Once again, exactly the same libraries that I would like to import. Now, what I'm trying to do is to load database, to select my data, to reshape my data from images 28 by 28 by 1. 1, it means that there are grayscale, so only one, let's say, color component is used. So I'm trying to flat this representation into that one. So I will get 60,000 data. Every data set is with this size. Then I will try to normalize my data. Instead values from 0 to 255, I'm trying to get, let's say, values from 0 to 1. Why? Then operations are more stable, faster, and so on. So let's read my data. You see, downloading my data. I'm trying to plot one example. So example number 0. So the first image from my data set, this is, let's see, 5. The true original label is 5. Now I'm defining the Keras model, the same as it was before, all the parameters, and then I'm executing the learning procedure, and I'm trying to store the history. And I will use this history to present the values of the mean square error metric values. So let's execute that. You see, the first epoch. Now, using the Keras API, we are training batches from the dataset and using each batch for each epoch. Okay, so we have 5. epochs. Perfect. You see our metrics, so mean square error is lower with every epoch. Now I can perform the same data pre-processing for test datasets as it was for training datasets, and I will try to predict the values of response variable using my test datasets and using evaluate from the Keras API just to calculate the, let's say, mean square error and loss values, but now for test datasets, so for the examples that were not used in training. So let's execute that and show the results. So you see, we have some results. What is our mean square error? Well, it's not very high. You see here, this is the calculate mean square error, another method to calculate that. So you see the mean square error for test datasets is very similar for mean square error during training. Okay, what is another example? I'm very sorry for fast presentations. I will, let's say, okay. So now, what is another example? Another example is almost identical as the previous. There is only one important difference. This difference here, the only difference practically. I'm not defining my own model. I'm using the definition of the layer, of the neuron, I would say, dense, with one neuron, one unit. This is my, let's say, linear operator with activation function, so with this nonlinear function input and specified input datasets. All other is the same. So you see, much simpler code. This is the code that I really need to perform training. This is the all. See, a few lines actually. All other code is the same. So I will not execute the code because of time. Okay. Of course, if we would like to get good results, we should use not only the accuracy or mean square error or some other metrics. The very popular metrics for classification are, let's say, recall and precision. It's not very, let's say, difficult tasks. I will skip it for now. You can find out about that from slides or from experiments that will be provided later. This is how we can calculate the precision and recall using TensorFlow. So I will skip it also. I promised to you that I will come back to this another definition of loss function, which is called entropy and cross entropy. Entropy is like similar to physics. Entropy from information theory is calculated like that. This is the sum of logarithm. This is the probability and multiplied by probability. As you know, the probability is from 0 to 1. So logarithm from value between 0 and 1 is lower than, let's say, 0, so minus. So that's why we are using minus here. Let's consider a simple example. We have, let's say, data set like that. We have 10 examples, 5 females, 5 males. So the probability to find a female in this data set is 0.5. Probability to find a male is also 0.5. So we can calculate here the probability of female, probability of male. So now we can calculate the entropy. 0.5 logarithm 0.5, 0.5 logarithm of 5. So the final is 1, the value of 1. This mix of instances. What if our data set consists only on, let's say, one category of objects? So we have only 5 instances, all are males. Look, we have, what is the probability of female? 0. What is the probability of finding male? Is 1. What is the entropy? 1 multiplied by logarithm 1 is 0. So you see, all instances are the same category. all instances here are different categories. What is the cross entropy? Cross entropy is the measure similar to entropy, but we are using two different distributions, P and Q. Sometimes we can specify the cross entropy as a entropy plus a Kullback-Leibler divergence. But this is maybe difficult, so let's introduce an example. We have two classes, okay? As so far, we have class 0, images with 9, class 1, all other images. Using test data, we calculate, let's say, probability of class 0 and probability of class 1. For example, let's assume that the probability of class 0 is 0.1 and probability of class 1 is 0.9. Using the build model, we can calculate or predict also our other probabilities. So the before probabilities are from test, the Q probabilities are from our model. So now we can compare the model and, let's say, true data. So if our model returns exactly the same probabilities, then we can calculate our cross entropy in the following way. P is 0.1, logarithm Q is 0.1, 0.9, 0.9. So our, you see, cross entropy is small. For another example, if our model gives completely different probabilities of results, then you see we will have the true probability 0.1, logarithm 0.9, 0.9 multiply logarithm from 0.1. So 0.1 is this one here from this model. So now we have a huge, let's say, cross entropy. And of course, we would like to minimize the cross entropy. So this is much better, of course. Okay, so far we discussed the binary classification. What about multi-class classification? Instead of sigmoid function, we can use another, let's say, activation function, which is called softmax. This is softmax. So as you see, we have different classes, K, so different number of classes, and we can use such kind of function. Very often in such cases, we are using special encoding, which is called one-hot encoding. We have 3 classes. Let's look here. If we have 3 classes, cat, fox, dog, we can encode them 0, 1, 2, or we can use a very special one-hot encoding. Please consider a cat. We will build an array, or with a one-dimensional vector actually, with total number of elements equal to total number of classes. So 3 classes, the size is 3. And then the values are either 0 or 1. If the index is 0 and the 0 is cat, so we will put 1 here, all other 0. For fox, the index is 1, so at index 1, we will put 1 here, all other 0, and so on. This is one-hot encoding. This is interesting for, let's say, softmax operations. Why? Because now, dear participants, we have 3 nodes, 3 nodes. Let's say 1 node for each class. For each class, we have operations like that. Look here, we have, again, parameters for 1 node, parameters from the second node, parameters from the last node. Then we are taking values from a particular example, image. We are feeding these values to 1 node, to a second node, and at the last node. From each node, you are getting this linear predictor value, the, let's say, sigmoid-like effect, but for a particular node. That's why it's softmax. So we will get probabilities. And now we would like to compare, we would like to calculate distances between those probabilities and, let's say, the one-hot encoded values. And of course, the smallest distance is our result, and the index at which we will have the smaller distance is our index for class. So we have a dog. So please, I will do the experiment, the final one, because I am already completed my presentation. So this is notebook, let's say 2.5, exactly all the same, but now I have number of classes 10. I'm using one hot encoding. I just can read data. Okay, I have, the time is over. Yeah, I know, 1 minute. Now I can specify my model. Again, I'm still flattering my data to get one-dimensional set of pixels, set of values. Now I have again dense layer. So I have 10 nodes because I have 10 digits. All the rest is actually the same. So finally, I can also produce my results and use for predictions. All other notebooks 2.5a is very similar. However, I'm using another loss function which is called sparse categorical cross entropy. So I'm not forced to use one hot encoding to encode my data. So my procedure, let's say, training is even simpler. Please look here. This is my model, number of classes, and I'm specifying my loss function, sparse categorical cross entropy, using logit, so automatically it will add the softmax operation, and all the other code is the same. And finally, please look at this final practically slide. What if my, let's say, examples are distributed like that? Well, if I'm using, one moment, if I'm using a simple case, a simple node, only one node like that, I can generate a line that could be used as a separator between two classes. So these are instances of one class, and these are instances of the second class. So my line model will be a borderline between two classes. But this is a very simple case due to the distribution of examples. What if I have distribution like that? Well, I cannot use one line. That is why I can use more nodes. Please look here, one node, second node, and the last node. So my input layer, data, my hidden layer, two nodes, and my output layer that combines the results from the previous nodes. So actually what I did here, I have one node, one line, second node, second line, and the combination of those lines. So now you see, I could generally specify the classifier. And of course, using the activation function in the end, I can specify how this borderline will look like to differentiate between one category instances and the second category instances. So that is what we call multi-layer perceptron, which we can use for many different cases, not only for images like MNIST, but also for CIFAR or other databases that you can make your own experiments with the code that I provided. That is all for now.